So welcome everyone to the LUCI seminar. Today we are very happy to host Professor Peter Grünwald. Professor Grünwald is a senior researcher in the machine learning group at CWI in Amsterdam. And he is also a full professor in statistical learning at the Mathematical Institute of Leiden University. Professor Grünwald's research is driven by a fundamental quest for safety in data analysis. And since as logicians we're interested in valid inferences, I think we are looking towards the same direction. So it is now really developing a kind of revolution in statistics, introducing e-values. And as he has also been recently awarded with the prestigious ERC Advanced Grant. So the title of today's talk is very provocative. E is the new P. And we are very curious to delve into this new statistical paradigm. So now I'll shut up and welcome again. Please, Professor Grünwald, the floor is yours.
Thank you, Costanza. Please call me Peter.
I am Esther, but it's fine.
It's fine. So yeah, the title is a bit provocative and maybe even a bit overblown, but it gets your attention, and that's the idea. So this is a talk about, you already said it, something called an e-value. And that is a relatively new concept in statistics, which has been developed by several groups. And my group in Amsterdam is a prominent contributor to that. And it serves as a notion of evidence. So evidence against a hypothesis about data, just like the p-value. And that's why you call it E is the new P, like the p-value. Let me start with a question. Does anybody of you know who this is? Actually, as logicians, you might have even a bigger chance of knowing this person than most statisticians do. So this is Leonid Levin, student of Kolmogorov, who's of course very famous for introducing the P versus NP problem. That's actually a very different P than the P I'm going to talk about. And he did that in an extremely famous paper in 1973. But around the same time, he also wrote the first paper in which e-values were actually existing as independent concepts. And that's the present paper from 1976, which is very obscure. It's actually even so obscure it was never translated into English. So that's kind of the start. And then nothing happened with this concept, or essentially nothing, until 2019. And then suddenly a lot happened. So my group, me with two members of my group, we wrote the paper Safe Testing. And that was where we showed that e-values can solve a problem of optional continuation, which I'll talk about today. A few weeks later, there was a paper called e-values. That was actually the first paper with e-values in its name. There was a paper by Schaefer called Testing by Betting. So Schaefer is also somebody who has worked a lot on the intersection between, let's say, reasoning with and without probabilities. There was a paper by Wasserman and Ramdas, Universal Inference, now all in top journals. And by now we have hundreds of papers, and we had 3 international workshops and many other things as well. So something's really happening here. And so this is a bit of bragging. I apologize for that, but I think it's important for you to know kind of the general background. So there are many groups around the world now working on this. But I guess the central group is the group of Aditya Ramdas at Carnegie Mellon University. And so Aditya writes a paper almost every week. Nobody knows how he does it. There are actually some rumors that he has a twin brother that nobody knows about. And he has won several prizes for this. And then there's my group at CWI in Amsterdam mostly. We also do a lot, not as much as Aditya, but a lot. And then there are many others, of whom there's one I would particularly like to mention. That's Volodyavov, because he's kind of the only one in the world who has worked on this between 1976 and 2019. And of course, it's not just us, it's also our group. Here you see current and former group members who've worked on this. Now enough about the bragging. What is going on here? Well, I'll first tell you a little bit about the classical notion in statistics of evidence, which is the p-value. I'll say a little, there are of course also Bayesian notions, which are different, and I'll say a little bit more about those later. So I start with the p-value because that's still the standard in statistics. And the e-value will turn out to be an alternative for the p-value. So like the p-value is measures something like evidence in the data against a hypothesis, which you can use to test a hypothesis. But if you think testing is boring, it's not just for testing. It's also, you can extend this to general uncertainty quantification. So there are always also, for example, confidence intervals based on e-values. And there's even some kind of alternative to the Bayesian posterior called the e-posterior. But I won't have time to talk about that. I will talk about the confidence intervals. And as we will see, the e-values are also kind of a bridge between, so classically, there are essentially two approaches to statistics. There's the frequentist one, which uses the p-values, and the Bayesian one, which uses prior distributions, beliefs. And the e-values can serve as something like a bridge. That was my phone talking, sorry. So I'll start with some of the problems with the p-values. So if you're not familiar with the definition of p-values, no worries. I will review that in a moment. I first want to go into like a high-level discussion. So, well, I guess most of you will have heard about this. So standard statistical testing, for example, in medicine. So you get a new medication or a new treatment. You want to see whether it works or not. You give a group of people the treatment and a group of people the placebo, and then you look at differences, for example, in blood pressure between the two groups, if you have a new medication for blood pressure, or how long does it take before a certain disease comes back, things like that. And then your null hypothesis is always the hypothesis that the medication doesn't work, the status quo, nothing's going on, and you measure the evidence against it with a p-value. If the p-value is small, you have evidence that something is going on. So maybe the medication works, or maybe some effect is there. And if that happens, you can essentially publish a paper or maybe even put a new drug on the market. Now, it has been known for a long time that there are problems with this approach. And so, for example, in 2016, a paper came by the American Statistical Association warning people that a small p-value does not maybe mean as much as people think it does. One has to be very careful in their interpretation and so on. And there are many other things like that. It's kind of generally acknowledged that there are problems with this. Now, there are many problems, but I will focus here on a specific one, or actually two versions of this problem. So this is the following. So suppose you test a medication and you get a promising but inconclusive result. So typically you say, I have enough evidence at least to publish, or to make a big noise about it if my p-value is smaller than 0.05. So let's say you get something which is around 0.05. It may be a bit larger or a bit smaller, but not very small. So then you think, well, this is promising, but we're not really sure yet that this medication works. And therefore, another group tries the same medication on a different group of patients, maybe in a different hospital or in a different country. And then, well, okay, it looks perhaps still interesting, but you're still not sure. So you would still try to get more evidence. So yet another group tries again on yet new data. And the question is, how should you combine these results? So the current method that people use, at least before e-values came around, is to just put all the data together and recalculate the p-value. But if you look at the definition of p-value, which we'll do in a moment, you see that this is actually wrong. And actually, sometimes this is even called p-hacking, because the effect of doing this will typically be to get more evidence than is warranted. So you will easier say that something is going on, that the medication works, then is warranted. So this is not right. But on the other hand, this is what happens all the time in medical meta-analysis, and the same thing in all the social sciences. Psychology journals are full of hypothesis tests, like how do people react to certain stimuli, etc. And when this is done a certain number of times, they do a meta-analysis where they essentially put the data together. But as we will see, this is just wrong. But then how should we do it instead? Well, essentially with p-values, it's impossible to do this in the right way. And in a moment, we will see why. Now, you might think at this moment that maybe this is only for kind of special cases that you do these tests more than once. But in fact, this is how science is done in the 21st century. And that is a part of where this problem originates from. So I'm not going to say p-values are bad or evil, which some people actually do say. They actually, if you use them the right way, they do their thing. But they were designed in a time when it was kind of inconceivable that you would just do one particular test and you would not do it again on different data and yet again on different data. Yeah, this was in the 1920s. Nowadays, when you want to put a drug to market, you have to do at least 3 different hypothesis tests. And they independently all have to give you a small p-value. But whenever a question is difficult, so if it's an interesting question, then the number of tests that is done over time is usually more like definitely more than 10. So for example, one case I know of is testing whether corticosteroids help against meningitis. There are around 30 clinical trials done on that. They still don't know if it helps or not. It's still controversial. And you have to think, especially in the medical sciences, this is not the big data world. So this is in medical testing with randomized trials are incredibly expensive because you have to make sure that you have to kind of have different groups of patients. The patients have to give consent. You have to make sure that the doctor doesn't know if he gives the treatment or the placebo. So it's a very expensive thing to do. Sometimes a trial usually costs like $1 million or something. And so if you do this 20 times and you still don't know whether medication works or not, you can imagine that there's a lot of waste going on. And that's actually one of the main concerns here. Current applied statistical science with testing gives a lot of what is called research waste. We have a lot of results which we don't really know what to do with and which were very expensive to obtain. So now I'm getting a bit more technical. How does this work formally? So the way we do this in statistics is we have a null hypothesis, and that's kind of nothing is going on, nothing special is there, the status quo. We have an alternative hypothesis that's usually something like the medication works or something special is going on. So the simplest example that people always use to explain the setting is you have a coin or some other randomness device and you want to check whether it's fair. So the outcomes are ones and zeros. You throw it a number of times. And then the null hypothesis, so that's this one, is just a single probability distribution, which says that all the points of probability one have, and they're independent. So the probability of any sequence would be 2 to the minus n, where n is the length of the sequence. The alternative says that the coin is biased. So you could either take a maximal alternative, where you say that it could be anything except 1/2. You could also say, so that would be θ1 equal to this whole set. It could also be like some particular subset. That's actually what you often get in medical testing. So in medical testing, we usually have the null hypothesis. Actually, we will see that on the next slide. So this is kind of the standard simple test in medical testing is you test whether a random variable, which you assume to be normally distributed, has mean 0 or not. So under the null hypothesis, you say it has mean 0. And under the alternative hypothesis, it has a different mean, where, for example, if you want to test whether medication works, you would say, like, under the alternative, the mean has to be at least 0.2 or something, because otherwise it's not interesting for medical purposes. So then the data could, for example, be the difference in blood pressure in a patient before and after he's treated with a medication. And under the null, you would expect to be no difference. But there's always noise, so then you would think it's probably normally distributed with mean 0. On the alternative, the mean is not 0. So I'm going to use this as my example throughout. It's called the Z-test in statistics. It's kind of the classical textbook example of how a test works. We're going to do it with known sigma squared. If sigma squared is unknown, it's called the t-test. It's a bit different. And now I'm going to introduce the p-value first informally. So the way you do this test usually is you look at n data points, and then you reject the null. And rejecting the null is just a strange terminology. It means you're willing to say that something is probably going on, that the null is, you might make a mistake, but statistically there's enough evidence to conclude the null is wrong. So the effect is there. And you do that if, with a normal distribution, you look at the average of the data, so that's this, and you reject the null if the average is in the tails, the 2.5% tails on the left of the right. So this is the distribution of the data if the null is correct. If the null is correct, it's just normal with mean 0. And if you get something with really too high or too low average, much larger than 0 or much smaller than 0, then you reject the null. And you typically do that when, so this is the typical threshold people use, 1.96 divided over the square root of the sample size. Why this threshold? That's exactly the threshold where if this happens, you're in an event with probability 5%. And this is equivalent to, if you define p-value in the standard way, this is equivalent to saying the p-value is smaller than 0.05. So you look at the average of the data, and then you look at what is the probability that the data is even more extreme than what I've seen, and that is called the p-value. So it's like if the data would be here, the average, then the p-value would be this area and the same area on the other side together. We'll define it in a moment precisely. And then you reject if the p-value is smaller than a certain value, which you set in advance. That's called the significance level, and that's usually called alpha, abbreviated as alpha, and we usually set it to 0.05, but there's nothing special in 0.05. It's just a convenient choice. So formally then, a p-value, I mean, if we don't work with normal distributions in the general case, a p-value could be any random variable, such that if the null hypothesis is true, the probability that it's smaller than alpha is smaller than alpha. This is the formal mathematical definition of a p-value, where usually if we want to use p-values which are good, we actually have an equality here. And that's what we had on the previous slide. The probability that this p-value, which was kind of the area and the tails under the null, is smaller than alpha, was actually precisely equal to alpha. But if it's actually smaller than alpha, we can still call it a p-value, and it's a conservative p-value. We see in a moment why. So then, how does it work? I'm going to recapitulate, and then I'm going to explain why we would do things like this, where the motivation comes from. So you have a null hypothesis, and actually everything I say now holds regardless of the alternative hypothesis. That comes in kind of only at a later stage. You set some significance level, and then you set a sampling plan. So this could be like, I'm going to look at 100 patients, but it could also be I stop when I've seen 3 ones. So it could be the data could have actually a varying length depending on what the data is. But in both cases, this determines an outcome random variable, which is the sequence of outcomes you observe. So in the simple case, we just said n is 100. This would just be a vector of 100 outcomes. Now you define your p-value on this random variable. So this is kind of, this summarizes the data. And now the data is actually generated. You look at all the patients in your hospital, you get to see this data. And then if the p-value is smaller than alpha, you reject the null. You're willing to conclude something's going on, and otherwise you accept it. Accepting it does not mean you think it's true. It just means you don't have sufficient evidence to reject it. So this is what people do in standard, in standard testing. And the question is, why would this even make sense? Well, now we get to the fundamental work of Nyman and Pearson from the 1930s. So Nyman is usually seen as maybe one of, or even the greatest statistician of all times. So they said, like, we can make 2 types of errors. We can reject the null if it's true, so saying the medication works even though it doesn't, and the opposite error, that's called the type 2 error. We can accept the null even though in reality it's wrong. And they say the type 1 error is, for whatever reason, we can get to that later, more important. So whatever we do, we want to make sure that the probability of making a type 1 error remains below a certain threshold. And that's where the alpha comes from. So if we set alpha 0.05, what we want is that no matter what is the true state of nature, what happens, the probability that the null hypothesis, so in case the null hypothesis is true, nothing is going on. The probability that we say it's not true, that we reject it, should be bounded by alpha. And by the definition of p-value, we know that the probability that we reject, that's the probability that p is larger than alpha, and that's just the definition of p-value, that is bounded by alpha. So we know that if we follow this methodology, look at the data and then reject if p-value is smaller than alpha, we make a type 1 error with probability at most alpha. And that's kind of the central thing. Everything else comes later. That's why we do things this way. And then again, but why are we interested in this probability of a type 1 error? Well, the next step is then to look at what happens if somebody does this, like a statistician. A statistician does this all his or her life. So maybe she works in a hospital and she does hypothesis tests for various different medications, and she always keeps the same alpha. Then every time she does a test, the probability that she makes a type 1 error is bound by alpha. So in the long run, if she does this all her life, then by the law of large numbers, with probability 1, she will make a type 1 error at most 5% of the time. So with enormously high probability, let's say it's actually completely sure that she will not make a mistake more than 5% of the time. And this was for Nyman. So Nyman also did have philosophical thoughts about this, which people don't usually learn when they learn statistics. But for Nyman himself, it was very important. He said that, the other people want to do testing in a Bayesian way, and they put probability distributions on the null hypotheses and on the alternative, and then use Bayes theorems. But Nyman said that's far too ambitious. We cannot really do that. The world is too complicated for that. If we would do that, we would be able to do real induction. We would be able to reason from a finite set of data. We would be able to say something about the probability that certain hypotheses are true. So he would say that's kind of real induction, you reason from the finite to the general. So he said that's impossible, but this is kind of a nice substitute. It's not induction, but inductive behavior. So we can never say in Nyman's philosophy about any individual test, what is the probability that for that data we make a mistake? It's not conditional on the data, which Bayesians say you can do. But Nyman says it's impossible. We can only say that if we keep doing this, then we will only make a mistake 5% of the times. So we don't do induction per sample, but in the long run, we behave inductively because our conclusions will not too often be wrong. But this is kind of the classical way of thinking about this, doing statistics this way. And in fact, if you take this strictly, then the p-value is just a tool. In the end, the output of your test should be just rejecting or accepting the null. That's what Nyman told us to do. But in practice, actually, people do mention the p-value. So they mention the p-value as an indication of the strength of evidence, because it's kind of clear that if you have like p is 0.04 or p is 0.00001, you somehow, in the latter case, you have a lot more evidence. But then the question is, of course, what does it mean? Because somehow this type 1 error guarantee, it relies on setting this alpha in advance. And so a small p-value, if alpha was big, what does it really tell you? And it's crazy, but nobody really knows. So actually, Fisher said that this alpha thing was kind of nonsense. He said you should just mention the p-value as a notion of evidence. And what people do in practice is kind of a mix between what Fisher said and what Nyman Pearson said. So Fisher is the other great statistician. Maybe Fisher is the greatest of all times, but Fisher and Nyman developed theories of testing at the same time. They both used the p-values, but they interpret it in very different ways. And that's one of the issues we have with the p-values. So now we get back to this problem I talked about, like one of the many problems with the p-values. So I said, like, what you cannot do is do a test and then do another test and combine the results. Why not? Well, here's an example. So you do a first test and you observe like 100 data points. Now, if the outcome is significant, you reject and stop. That's the normal thing. But let's say we are in a very simple case of this optional continuation. We will maybe continue to a second test under certain circumstances, but only a second. We will not go a third or a fourth or so. So maybe if the first test was not significant, then we will go on and do a second test on a second batch of data, maybe in a different hospital. And then if it's significant, we will reject the null once again, and else we stop forever. So now we accept the null. Now we know why this cannot work. Because if we use a strict p-value, like the one in the normal distributions I showed you before, then for this first test, the probability that the p-value is smaller than 0.05 if the null is true. So the probability of a false alarm, a type 1 error, is 0.05. But what we do here is, if we're in this case, we make a type 1 error, we stop. And if not, we kind of give the data a second chance. So on many data sequences, we will actually go to a second data sample. And then the total probability that we reject a null, so that's the probability that we conclude there is an effect, even if there's none, must be larger than 0.05, because it's already 0.05 if we stop here. But now with a certain probability, we don't stop. We go on, and if with the second batch of data, you get a small p-value, we say after all that we reject. So this probability has to be now strictly smaller than 0.05. Statisticians say we have spent our alpha in the first round. Somehow every time you make a reject decision, you spend some of your significance level. And it's actually easy to show that if you keep rejecting this doing this for more than 2 times, then rather quickly after like 50 batches or so, the probability that you reject is almost 1. So even if the null hypothesis is true, you will almost certainly say it's wrong. So this is why this optional continuation thing doesn't work. And now this is kind of the story I tell to statisticians, but actually for an audience like you, it's nice to add something, because this is actually philosophically interesting, also in a different way. There's another problem. It's not just that you cannot do this. It's in some sense the problem is much worse. And to explain this, let's consider a variation of this. So suppose you're the statistician and you observed that on the first sample the p-value 0.11, and you tell your boss that the evidence is promising. It's relatively close to 0.05, but not significant. And then your boss gets enthusiastic and says, well, we're so close, let's get some additional data. Let's do a second sample. So now you're worried because you know that this is not right. We've just seen that this is not right, right? But then you tell your boss that actually it was, you now tell your boss the details, that it's 0.11. And then your boss changes her mind and he said, well, that's so much larger than 0.05. Let's not do this because the second samples may be expensive. Let's just stop anyway. So now you can stop and accept the null. So the question is, if your boss actually decides not to continue sampling data, should you be relieved? And now it gets paradoxical because the answer is no. This is still wrong. And this is really weird because if you see this, you exactly followed the protocol that the correct protocol, but still the result has been invalidated merely because what this means is there would have been some data on which a different decision would have been taken, on which you would have gone to a second sample. And even if on the sample you actually see you don't do that, if it happens counterfactually on a sample you didn't see, that already invalidates the type 1 guarantee. Because what happens in this scenario is there is some data, you just don't know which data, but there's some data for which you go to a second sample and you put the results together. And as soon as there's some data like that, the total probability of making a mistake is larger than alpha, larger than 0.05. So your error guarantee is validated. It's invalidated. So this means that even though you might follow the protocol correctly on the data you see, things still go wrong if you would have done something different on data you have not seen. And this is really funny, of course, because it means that the validity of your p-value depends on things which are counterfactual, what would have happened in a situation that never occurred, and which are often like unknowable because you cannot know what would have happened if the data had been different. And if you think of p-values just as evidence, this is a problem because it means that it would be a very strange notion of evidence because it depends on your actions in situations that did not occur. And you would say, how can evidence depend on something which you would have done in a situation that not occurred? It's just strange. But it also destroys this Nyman-Pearson view. And so this is a second problem. Both problems, optional continuation, this problem are solved by the e-value. How does it work? Well, if you calculate an e-value instead of a p-value on your samples, it works kind of similarly, but you can multiply e-values over samples, and the product remains an e-value, no matter how often you keep doing this, and no matter what are the rules for continuation and stopping. It's completely robust against whatever the rules are, so you don't need to know the rules. Well, it also solves several other problems of p-values, but not all, so it's also important that there are some problems it doesn't solve. But I'll only talk about this optional continuation and counterfactual knowledge. So then it's time to define the e-value. Already have in my talk, but so I thought it's important to give like an overview of the issues here. So an e-value is the value taken by an e-variable, and an e-variable, now I'll assume for simplicity that every test has a fixed sample size, let's say just 100 patients or something, is a non-negative function of the data such that under the null hypothesis, if the null hypothesis is true, the expectation is bounded by 1. That's all. So every function with this property we call an e-value. Notice includes trivial function, like the function which is always 1, right? That says expectation bounded by 1. It just ignores the data, and that's a useless e-value. So we need to look at what are useful e-values. That comes later. How can we define how can we interpret e-values? Well, the first interpretation is as a p-value after all. If you have an e-variable, then the reciprocal, so 1 over, is actually a p-value, but it's a conservative p-value. So for the p-values we saw until now, this inequality held actually with equality. But for e-values, this is usually a pretty strict inequality. So there is some room in between alpha and this, and that room is crucial. That room makes sure that you can multiply these e-values and still get something meaningful. Now, why does this statement hold? So this is just a definition of a p-value. Well, this is just Markov's inequality. So we know that for non-negative random variables, the probability that they're large is always bounded by their expectation divided by the thresholds. So in this case, that would just be alpha. Intuitively, they're non-negative by definition. They have expectation 1. Then the only way in which that's possible is that if the probability that they're large has to be small. Now, because 1 over the e variable is a p-value, you can actually test like with p-values. So we call the e-based tests just the same thing. We reject the null if the e variable based on the data is larger than 1 over alpha. So we still have significance levels. And so typically we would, for example, again, take 0.05. And you get type 1 error guarantee of 0.05 if you work like this. But in general, it will be a bit more, this will be more conservative than what you get with p-values. So you need more extreme data to reject the null with an e-value than with a standard p-value, because you have an inequality where the p-value you have an equality. So here actually you see a picture of Nyman, who might have liked this after all, because you can do testing basically just like with Nyman-Pearson, and you have the type 1 error guarantee, which is what Nyman really wants. So then how does it relate to Bayesian testing? And now it gets interesting. So how do Bayesian statisticians do testing? Well, what they do is they put a prior distribution on all elements of the alternative distribution. So this would be, for example, all biased coins except 1/2. And They would also put a distribution, also called a priori distribution, on all distributions in the null, and then they would take the likelihood ratio as their measure of evidence in favor of the alternative. The larger this is, the more evidence for the alternative. Why? If you would have equal priors for the alternative and a null, equal prior distributions, 1/2, 1/2, then by Bayes' theorem, you would have that the posterior probability of the alternative divided by the posterior probability of the null is equal to this. That would follow from Bayes' theorem. So this is why a Bayesian would think this is a right notion of evidence. It tells me how to get from priors on hypotheses to posteriors. So this is much more closely related to the e-variables than you would think. Because if you have a simple null, which was the case in all the examples we saw so far, then this Bayes factor actually is an e-variable. Why? Because its expectation under the null, that would be given by this integral, because expectation is just an average under the probability distribution. So then the distribution of the data under the null cancels. You get an integral of a probability distribution over all data, so it's 1. So whatever distribution you put on the alternative, this Bayes factor, which the Bayesian uses as evidence for H1, is an e-variable. So in fact, Jeffries, who kind of pioneered Bayesian testing, might have liked this, because for simple nulls, Bayes factors are actually e-variables. But unfortunately, I don't have time to go into this for composite nulls. So if this is really a set of distributions, it changes completely. And then the Bayesian methods and the e-value methods become different. And most tests we do in practice are actually with composite nulls. So then this is also like a set. So how do these e-values, so now we've seen some examples, how do they solve this optional continuation problem? So here I kind of formalize it. So you have different samples of data. And for each data, you also have some side information. So this could be, for example, my boss has money to recruit more patients, things like that. They're non-random in general. For simplicity, we assume that all data are independent. So every Y is really a sample of patient data, for example. It could also be just a summary, so then it would not be a vector, but it would itself be just one number. That doesn't matter. We do have to make some assumptions, and the main assumption is that so this side information, the data is new data, so the jth batch of data, this would be like the jth hospital in which we look for data, is independent of the previous data and also the previous side information. So the side information cannot be like, I know that on the future data you will get this and this result. Then everything fails, of course. Now, under these assumptions, if you do the following, you have some e-variable, which is defined on the first data batch. And then if the outcome is in some range, you go to the second data batch and you calculate another e-variable applied to the second data batch, or you stop. And after the second data batch, you do the same thing. If the data is in a certain range and the side information has certain values, you go on, otherwise you stop. And you keep doing this, and at some point, you really stop. And then you report as a final result the product of the e-variables. Now, the central result of this whole e-variable world is that if you do this, that any e-variable you can get like this, that any product you can get like this is itself an e-variable, independent of the stop continue rule that was used. So actually, you don't even need to know the rule. It could be just that your boss looks at the data and said, well, given this data, I think we should look at 10 more patients in a different hospital. That's fine. So you don't know why your boss made that decision. No matter how that was done, this product is itself an e-variable. And because it is itself an e-variable, it has expectation bounded by 1. This means that the probability that the product is going to be larger than, say, 20 is smaller than 0.05. No matter what the rule was for continuing or stopping. This means that we have a type 1 error guarantee. So like Nyman wants us to have, the probability that you make a mistake if the null is true remains bounded by alpha, no matter how often we multiply these things, right? Because the probability that once we finally stop, that product has expectation bounded by 1. probability that is large is small. Now, if you want to prove that, you can use that using martingale theory, but well, there's no time to do it here, but there's essentially, it's exactly the same math, which tells you that if you put money in a casino, then no matter, and you every time you gamble in the casino, and then you re-gamble everything you won, right? So everything that's left, you put it on the table again in some way, and then you get some money back, you lose some money, you re-gamble. Then it's also clear that the expectation of the money you gain, if you start with $1, the expectation always remains bounded by 1. You don't expect to gain any money, no matter what your rule for stopping is. So even if you say, I'm going to go on until I have either $1,000 or I'm bankrupt, or either $1,000 or it's Tuesday, expectation remains bounded by 1. It's the same math, which also makes sure that in a casino, you don't expect to gain any money. So let me just skip this, given the time. So a corollary of this is kind of a nicer way of perhaps putting it, is that you can actually look at what happens if you keep doing this potentially forever. So you keep looking at different data and you multiply e-variables. And basically, you assume that there's always new data available. Then the probability that the product will ever get larger than 1 over alpha, so if you take alpha 0.05, the probability that this gets ever larger than 20 remains bounded by alpha. And this corresponds to the fact that in a real casino, if you start with $1,000 and you always reinvest, the probability that you will ever reach $20,000 is bounded by 1 over 20. And if you, this is actually something you could easily try out yourself in a casino, and you will see it is true.
Sorry, I have just a curiosity on this. Do you need an assumption of an infinite capital for this to work?
No. Okay. You do need assumption of infinitely divisible capital. Actually, if it's not infinitely divisible, it's actually worse. It only becomes worse. So this becomes strictly smaller than alpha. But this theorem assumes that in a casino, you can basically put like 0.3957 cents on red if you want. But okay. We're assuming that you start with, this is kind of assuming that you're not allowed to borrow money in this setup. So you start with $1,000 maybe, and you can never go below 0. So there's no infinite capital. That's kind of, there are different games where you have that, but in this kind of the e-variable game, it's always like positive. Capital starts and stays positive.
Okay, thanks.
Okay, so this is kind of the basic story. Are there any other questions on this? Because now I want to say a little bit more about some more details, but maybe this is the right time. I don't see any hands, so then I'll just continue. Now we're going to go from test to confidence intervals, and that's partly because then the difference to Bayesian methods will become a lot clearer if we do this. So, of course, maybe this is not an audience that's familiar with confidence intervals, so I explain in a moment what they are. So the first, but I'll first kind of walk my way towards that. So until now, we played a game on the level of batches. So we had like 100 patients in one hospital, 100 in another, etc. But we can also define e-variables per outcome. So that's just something which is defined on a single outcome, and it is expectation bounded by 1. And if we have a sequence of outcomes, we can use different e-variables for different outcomes. We were actually also, like in the previous slides, I already showed you that basically the function you use for your e-variable, it has expectation bounded by 1, but the definition of the function may depend on everything you already know, so everything in the past. So that's the same here. And if you do this, you again have this Fields inequality, but now it's on the level of data rather than batches of data. So if you have the e-variables defined per data outcome, then if your null hypothesis is true, then the probability that the product of E variables will ever get larger than 100 is bounded by 0.01, no matter how long you keep trying. And such a product of E variables is called an E process. This is an aside. Oh, why am I telling you this? We can use these E values per outcome and their products to define something which has been called an anytime valid confidence interval. And it works as follows. So again, assume I have a simple null hypothesis. So this could be, for example, be the data are normally distributed with mean theta. It's just a single distribution. And now I have a whole collection of these E processes, so products of E variables. Let's just say I use the same one for every outcome. So this could, for example, again be a Bayesian likelihood ratio, a Bayes factor. Then I know that the probability that this product will ever get larger than 1 over alpha is bound by alpha. And that holds at the same time for every theta. Now I define my confidence interval at sample size n to be the set of all theta that if I would think of them as the null hypothesis, I could not reject. And so I basically play the same game as before, but now I play it at the same time for every theta apart. So I have many null hypotheses, and for every theta, I say I'm going to try to reject it. If it's the corresponding product is too large, I'll reject it. And then here in this set, I keep everything that I could not reject. And then because I have Wills inequality, I get that the probability that there will be some sample size at which the true theta from which the data are sampled is not in the confidence interval is bounded by alpha. Because the probability that I will pull it out of the confidence interval is bounded by alpha for every theta. So the probability that I will ever pull it out, so the probability that it's not in here is bounded by alpha. This may seem very abstract, so let me give you an example. So what I did here is I sampled data from a normal distribution with mean 7. And I made the anytime valid confidence interval based on the standard E variables for Gaussian distributions with mean 7. And at each point in time on the y-axis, you see the width of the interval. And then of a 95% confidence interval. So that's the blue area. Inside there is the yellow area, and that's a standard confidence interval. Now, a standard confidence interval, that's something you have all seen, for example, during COVID, when there was all this talk about the value of R on the news. So a standard confidence interval is an interval defined such that the probability that it contains the true parameter is at least 95%. And the standard confidence interval for normal distributions is made by taking the average of the data plus or minus 1.96 over square root of n. We've seen this number before because basically what we do is for every mean, we make a separate test. Can we reject that mean at the alpha level? And if we can, we take it out of the confidence interval. And then only only the data for which the mean is inside this interval cannot be rejected. If you do that in time, you get the yellow interval. So that's the standard confidence interval. And you see that if the data is generated from a normal distribution with mean 7, then the standard confidence interval gets narrower and narrower and goes around it. But sometimes it does not include the true parameter. It's sometimes the true parameter goes out because we know at any particular time the probability is 95%. But the standard confidence interval is again made for a fixed sample size, right? A fixed n. So if you take a random time, say 250, and you check, then the probability that the black point is not in the yellow interval is 5%. But the probability that the black line will sometimes go outside of the yellow interval is actually much larger. It's actually 1. So because the standard confidence interval is made for a fixed time, if you use it at many times, then you know for sure that at some point you will just fall out of the interval. Now, the anytime valid confidence interval, based on E values, has been made so that the probability that the true mean will ever fall outside of this interval is bound by alpha. So in this example, it actually never falls out. Of course, it can fall out, but for any individual run, there's a probability of 95% at least that no matter how long you go on, the blue interval will still contain the black line. So it's a lot more robust, right? The blue interval is wider. That's the price you have to pay. There is a price to pay for this robustness. But you win a lot because you know that you can look at the data as often as you like. It's anytime valid. No matter when you look and for what reasons, the probability that you find the true value in the interval is 95%. So how do you make these? Here's actually some numerics. So the standard confidence interval looks like this. And if I make this interval anytime valid based on E variable in a standard way, it looks like this. So it has a log n extra width. But it's kind of similar. It's always wider, but it's similar. Formally, remember that we said that base factors are E values for simple nulls. And these are actually the E values we use. So the E values we use are of the form, the numerator is p theta, so that's a normal with mean theta, and the denominator is an integral, it's an averaged probability density, where for the average, here we also take a Gaussian prior. So this is what we used here. Wait, well, I go too fast now. So this looks similar to what a Bayesian would do. But now actually, so in testing, it was really it was actually the same. But here in these intervals, it's actually different because if you ask a Bayesian, what is the 95% probability interval of theta given the data, the Bayesian would just report this posterior probability. That's the Bayesian posterior. And that's not the same thing as this thing. So it's different. And you can show that the Bayesian, if you take the same prior, then the Bayesian interval is always narrower. And in fact, here in this example, we took a standard prior with a high variance, and the Bayesian 95% interval here is indistinguishable from the yellow band. So we're always more conservative. Even though we also use a prior, right? Because we use this E value definition uses a prior in the numerator, right? That was this the one you see here. So then you wonder, like, what exactly is the difference? And that's the last thing I want to tell you. So that the criticism of Bayesian methods is always that they have the subjective component. You have to put in a prior density on the parameters. Like you say, the data is normal, and I somehow have to represent my beliefs that it's normal by a prior density. Usually you also take that to be normal, but it has to have a certain mean. So that corresponds that you think that a priori, before seeing any data, you expect your data to have a certain mean. And of course, in reality, you often don't really know. So we also use a mean, but our E values have a frequentist interpretation irrespective of whether the prior is correct or not. So then it's interesting to see what happens if it's actually not correct. So you might wonder philosophically, what does it mean to have an incorrect prior? Because it's subjective, but let's say we just do simulation and we know what it means. We simulate data from theta 7. So we simulate data from a normal distribution with mean 7, but we have a prior, which is a normal distribution with mean 0 and variance 1/2. So the prior thinks the mean should be 0. In reality, it's 7. And we use the same prior to define our E variables. And then the picture looks completely different from before. So the meaning is the same. So the blue is the anytime valid based on the E values, the anytime valid confidence interval. The yellow is the Bayesian interval. The data comes from mean 7, so this is the true mean. And now you see here that the Bayesian interval is just flat wrong in the beginning because your prior assumptions were wrong. The data comes from something with mean 7, but you think the mean was 0. So you're just very confused, and you put a small interval which clearly does not contain the true value. And it's slowly, as you get more time, the data becomes more important and overwhelms your beliefs. So at some point you become kind of right. Now, the anytime valid confidence interval is actually not wrong, but it goes wider. So if the prior is more or less okay, then they are very similar. The blue one is just slightly wider than the yellow one. But if the prior is very bad, then the blue one becomes very wider. So it's still worse than before, but it's correct. And so this is a very important philosophical difference. If you use a bad prior in in a Bayesian method, you just get bad results. If you use a bad prior in an e-value based method, you get more uncertainty. So this is philosophically different because you do have a subjective component, but you still have kind of objective conclusions. They just become more uncertainty if your subjective component does not align with the data. Actually, this idea is not new. It's just with e-values, you can very nicely formalize it. And it has been called like instead of, so they say Bayesian statistics, they really believe some things about their parameters. And here you're more into, you really like, it's more like a hope that you will be lucky on your data. So you also have beliefs, but you don't really believe them. It's just like they might be kind of correct, and then you're lucky. If they're not correct, you're unlucky, but you're still not wrong. Now, given the time, I will skip the final part. Just want to say that in a way, all the mathematics gets really interesting if you look at big hypotheses, null hypotheses. A simple example is the t-test, which is also you want to learn the mean of a normal distribution or test the mean of a normal distribution, but you don't know the variance. So that this would mean that your null hypothesis is every distribution with mean 0, but all possible variances. And that makes the problem mathematically a lot more complicated. And all these advances of the last 6 years were mostly on these composite hypotheses, because there it's not so, base factors are not e-values anymore, so it's not so clear how to make them, but now we know how to make them. And then, well, to end, so we have a notion of evidence here in terms of e-values that's at the same time more robust because you can do more things with it and it will still be valid, and more flexible because you can do more things with it than p-values and base factors. You can do the optional continuation, and you also avoid these paradoxes which rely on counterfactuals, which you have with p-values. Now, of course, I mean, it's not, despite the title of this talk, it's not perfect. There must be a price to pay. And the price to pay is here that we saw that in these intervals, the confidence intervals are always wider, which means that you inherently have more uncertainty if you use e-values instead of p-values. And in practice, that means that you will need a bit more data to get to valid conclusions, because your uncertainty becomes less and less as you get more data. So to get a certain required uncertainty, you just need a bit more data. So as I said, there are many, many papers around this now, and my most of the energy goes to making e-values for complex statistical problems like logistic regression, things like that. But actually, it's a part of my ERC to also look more at these paradoxes. There's this thing in statistics called the likelihood principle and Birnbaum's theorem, which basically says that every notion of evidence should be based on likelihood ratios. And it's actually not so clear if that is the case for e-values or not. That's a complicated question because in simple cases, they always are likelihood ratios, but in complicated cases, they're still very similar, but not exactly the same. So there's a lot of stuff that can be done here and questions which are wide open. So that was my talk. Thank you very much.
Thank you very much. So,
nice. I see. Applause.
Applause, yeah. Let me stop the recording.